All right. So quick recap about the yesterday lecture on partial observable Markov decision process. So we've seen that there is a way to merge planning with inference by introducing this notion of partially observable Markov decision process. And the key conceptual objects that we have been introducing is this notion of a belief, that is a probability distribution over states. So the agent assumes that it has no direct knowledge of the states, but it has only indirect information through observations, Y for us. And the agent has this inference device, which is Bayesian inference, adapted to the situation where there is an underlying hidden Markov process, and uses this combination of these two notions, a belief and an inference, to construct a decision process, that is picking actions based on beliefs. I didn't show you all the math, but I sort of introduced the main idea for solving PMDPs, is that to realize that a PMDP is nothing but a Markov decision process in the space of beliefs, in which the transitions between different beliefs are given by Bayesian inference. Okay, so it's a rather abstract view, which we will try to make concrete in one specific example today. It is nevertheless quite a powerful formal approach, because it allows to write down Bellman's equation for partially observable Markov decision processes, which has the same, roughly the same structure of the ordinary Markov decision process Bellman, as it should, because it has to reduce to it in the case where states are actually detectable, measurable. So in the specific case when the observation function here, okay, the probability distribution for observation, if it collapses onto delta functions for the states, that is, observations are states themselves, then all this expression simplifies. The beliefs go into the corners of the belief space, that is, you get perfect knowledge of where you are at every time, and then this exactly reduces formally to the customary Bellman equation for Markov decision processes. Okay, so we highlighted the big difficulty is that this equation now is a functional equation, non-linear functional equation, because the value function is not a vector any longer, but it's truly a function of a continuous space. So, like I told you yesterday, but it's good to say that again today. So, how do you go about trying to solve directly this equation? So there are some techniques which are relatively recent, okay, that try to solve this equation. So to fix the ideas, let's consider for a second one of our workhorses, that is just a system with two states and two actions. Okay, so the most general one, there would be probabilities, etc. So I'm not detailing all the transitions here, but you've seen this already several times. So what is important here is that your belief space, okay, since there are just two states, your belief space is one-dimensional, okay, and goes, it's just an interval from 1 to 0. This is your belief space. Why is that? Because this, you can think that this is the probability of being in state 1. And of course, the probability of being in state 2 is just 1 minus that. So there's just one single real variable comprised between 0 and 1 that describes the belief space. So one general idea that I will just describe to you very qualitatively, because it's a generic approach to try to solve the Bellman's equation for PMDPs, is that you construct a finite set of points. Okay, so this approach is called finite point, or just point. Let's say better. Point-based value iteration. So the idea is very simple. Is rather than working with a full segment, we choose a certain set of points here. Okay. And we try to solve our Bellman's equation basically only on this set of points. That's the underlying basic idea. So in order to have a manageable set of beliefs. Of course, these beliefs that you choose here, beliefs, must be reachable. Okay, this means that if you start from your initial belief, which might be, for instance, 1/2, 1/2, if you have 50% prior on where you are in space, given the states and observations, you must reach one of those beliefs in a set. So one way to construct this, for instance, is to run forward our model and therefore pick some policy, for instance, at random. So you pick an action at random and you make an observation. You end up in a state and pick another action, another observation. And if you add all the new beliefs that you have obtained by iterating, clearly you get lots of points. Okay, because at every step you can take 2 actions, you can make 2 observations. So from 1 belief, after the next step, there will be 4 beliefs. And after 2 steps, there will be 16. Okay, so after 10 iterations, you end up with 1,000,000 beliefs. Okay, and these, of course, do not exhaust all the possible beliefs, but they provide you with a set of points here, which is sort of a starting point for trying to use value iteration on those points. Okay, and then you use other ideas. And the next important idea is that if you try to plot the value function in this belief space, well, it has a shape like this, more or less. Okay, so you can actually prove that this value function, this is the belief, and this is the value function, optimal value function for the belief, is always a convex function, like a druid. And so one idea is to approximate your value function with a piecewise linear function, which is based on these points here. So this is another important idea qualitatively, to replace a continuous function with its piecewise linear approximation. And then you start and you do 1 iteration of your value. And then after that iteration, you have to do other technical operations like pruning and enriching your space of beliefs. So some beliefs that are at which your value function is not suboptimal, you just remove them, and you look for other beliefs where you want to improve your approximation. Okay, so it's a very complex algorithm. The basic ingredients are these ones: work with a finite set of points and use piecewise linear approximations. And then there are lots of technical results. For those of you who are interested, I can point you to a reference. Okay, so this is just to convey the message that there are algorithmic ways of approaching the solution of a PMDP in rather large spaces also. Okay, so it's important to know that, but we will not go into the details. What we will do today is, like I told you yesterday, there is a subset of problems which lend themselves to a much easier treatment. And these are the problems in which your transition probabilities and your observation models are, in a sense, simple. So they belong to a class of likelihoods and transitions which are described by simple probability distributions. And there exist conjugate classes of distribution of priors by which the Bayesian updating leaves them in that class. Okay, so this was a highly formal statement and involved to say just in words that if the beliefs are Gaussians the transitions are Gaussians and the likelihoods are Gaussian, then the new beliefs will be Gaussian. And we can solve the Bellman's equation not in the space of probabilities, but in the space of the parameters of the Gaussian, which is much smaller, of course. We will not do this today. What we will do this today is we'll discuss the problem of Bernoulli bandits, that is coin flipping, deciding what coin to flip. Because in that case, the transition probability is simple because it's just a unit. Okay, it's the identity. States don't change. And the likelihood to observe an outcome is Bernoulli. And if we, as we will see, if we use beta distributions for the beliefs, we can write down this Bellman equation in a much more simple form and solve it. Okay, so that's the plan for today. If there are any questions on this sort of broad framework, please do not hesitate to ask. Otherwise, I'll leave the floor to Emanuele, and I have to make you host, which I will do immediately.
Okay, so I will share my screen.
Okay, you're the host now.
Okay, perfect. So thanks for being here in the introduction. So today, as we just saw, we will deal with the two-arm bandits in the case of partially observable system. So it's now I've split the lecture in two, but the timing is completely random in the sense that we will have a break in the middle, but I'm not sure when this middle will be. Please ask all the questions, and if at a certain point you are exhausted, then it's a good place to make a break. In the first part, we will see in this very specific case how these ideas of belief of Bayesian updates and are in a concrete way. So first we will we'll see, okay, we have this system of coin flipping, what we know and what we don't know. So we will lose our complete information of a state. So we will introduce the beliefs. We will see what actually are these beliefs and how to deal with them. And we will exploit this fact that Bernoulli and beta distribution are conjugate to have a complete picture of how to deal with beliefs. Then most probably we'll have the break. The second part is that we will use all this information we've gathered to transform this non-dealable system of a partially observable two bandits, Bernoulli bandits, into a rather simple Markov decision process in the belief states, space states, and we will use basically some technology we already have to solve it perfectly, exactly, not exactly, but in a rather controlled way up to the end. So let's start with the description of the problem. So we have a two-armed Bernoulli band. You will have seen it several times by now. It's a standard. Let me increase a bit the size. Okay. We will have just this simple system. We have only one state. So we are dealt two coins, and one coin, which is called action 1, has the probability Q1 to give me a success with a reward of 1, and a probability 1 minus Q1 to give a reward of 0. The second coin has a different probability, but it's the same. So both coins have Bernoulli, so 0, 1 with some probability. And of course, my aim in life is to maximize the reward in a long term. Now, as you can see, since we have two coins with two different probability, and we assume from now on that the two coins are perfectly independent one of the other, there is a whole space of possible cases, of possible states, which are the the couples of the two probability. In particular, it's, we have this with square here, 0 to 1 probability of one coin, 0 to 1 probability on the other coin. Each point in this space corresponds to one precise realization of the two arm bandits. For example, this point here is the one in which I've dealt two coins, both very fake, and they only give fails whatever I do. So 100% probability of giving fail for both of them. This here is one with Q2 is equal to 1. So Q2, the second coin, always gives me a success. But the first coin is a probability of 0.5, which means that 50% times fail and 50% success. So whenever I am in a specific point, my options are very clear. I will just try to maximize and use only the coin with a best probability. Of course, we are now in the problem where we don't know everything. We don't know everything because we will see we don't know exactly where we are, but we know a lot of things. So this is a case in which I have a partially observable and we are model-based. So we perfectly know how the system works. So what is known? For example, the first thing which is known is that when I have fixed the Q1, Q2, I know how the reward of the function is dealt. So if I know the state, the reward function is perfectly known, and it's a Bernoulli, as we said. Essentially, the probability of having a result. For example, if I have Q1 and Q2 and I choose to act with the first coin, is this here. So A is just a normalization. Forget about it. It's important because we will see many times I have a Q1 to the R. So if it's a success, QR to 1. 1 minus Q1 to the 1 minus R. So if it's success, this goes to 1. And if it's a fail, so if it's a success, it's Q1. And if it's a fail, 1 minus Q1, as we said. We know that it's the same exactly thing for the second coin. So this is known fact. So then another thing which is known, which also Antonio pointed out briefly before, is that there are no transitions. So whatever I do, whatever coin I decide to flip, the state will not change. So this turns out to be this condition here. So the probability of transition from one state to another state is 0 if the two states are different. And you will see, if you go back to all the theory described yesterday, whenever you have an equation in which you have a sum over S prime and you have probability of transition, that is simplified because that sum goes away. Only transition between S and S and only transition which remain in place are allowed. And this happened with probability 1. So this is known, and it's a very simplifying fact of life. Second thing, it's known what the outcomes of the actions are. So this is the case yesterday also. There was this thing, the observable of a state or the percept. So we all know the information about the rewards, essentially, which are the outcome of the actions. And we also know with model for their observation. So given, we know given a state, what is the model for the rewards, which is essentially the same as before. It's the Bernoulli distribution of the reward. So we know a lot of things. What we do not know is the state. So we are not given the information of what this probability Q1 and Q2 are. That is absolutely out of our point. We have not direct information about that. We need to extrapolate this information from other things. So the idea is, as we as pointed out in this series of ideas, is that we have to shift from the idea of a single state to the idea of beliefs over state. And a belief is just a probability distribution over the states, which means that I am not given the information that I am in a perfect state here in a point, but I'm given, I may have the idea that I have a distribution of them. Not all of the states are equally probable. Basically, this means that instead of having a state, I have a function over state. And this is a typical example of a belief. You can see purple means I have my belief is that I'm not there, and I have a maximum probability of being in a certain point. Okay, so instead of this is a typical belief. Instead of being in a state, I will deal with probability distribution over a state. Notice that this is something which you have done yesterday, but it's rather I think useful to now that you have to think that instead all which could be dealt with state now have to be integrated in the belief. So for example, if you have a probability of having a reward given a state, now you have a probability of having a reward given a belief, which just means that you have to integrate or sum over all the state given the probability of being in the state, which is the belief. So it's a complete shift from being in a single point to having to evaluate or average out over all the probability of being in all points. Okay, so but once we are in the belief, this is a general thing that now that I have some gut feeling, which is not a gut feeling, it's mathematical result of what I see. I have a belief of where I am. Now, as always, I have to do two things. I have to, I can explore, which means I have some idea of where I am or what my belief is, but I want to make sure that my belief is more accurate to have a better understanding of where to go afterwards. Or I can exploit. So my current belief, it says that I should do this action here is the best one. So this is the action I have to take. And as always, we will have to find a compromise between the two, so that I explore as much as I can to make my belief stronger, and also I have to exploit my beliefs so that I do what I currently think is the best thing. Okay.
May I add just a comment? So if you go back to your picture of the typical belief, yeah. So for instance, there a strategy that exploits your current information would be to say, okay, let me identify the maximum of this belief. So the point where the probability is maximal. And then I say, okay, I fully trust that my state is the one where the maximum is reached, and therefore I act accordingly. So in this case, the maximum is above the diagonal, which means that at that point, Q2 is larger than Q1. And then according to that, I would play action 2. Okay. Now, this is provably suboptimal. Okay. And the reason is that sequences of observations might have carried you to a point where it's just due to incomplete information about the system. Okay. Just because out of bad luck, perhaps the number of times that you've won on one arm is larger than what the actual mean. Okay. On the contrary, what is an exploratory strategy? For instance, an exploratory strategy looks at this figure and says, oh, it's very broad along the Q2 axis. Okay, so maybe I have to sample Q2 many times because I want to make it sharper. So I have more uncertainty on Q2 than I have on Q1. So a very exploratory strategy decides I have to play Q2 in order to reduce my uncertainty on Q2. Okay. In this case, the two things coincide, but in general, it's not the case. It's also provable that this kind of purely exploratory strategies, so strategies that look only at information rather than looking at rewards, are suboptimal as well. So what is optimal and what Emanuele will compute is the sweet spot between exploration and exploitation. Thank you, Emanuele.
Okay. Good. Okay, so and now we want to deal, and we will arrive to this sweet spot. So the idea is that we need something more. So we have seen that we have, as Antonio said, we have our beliefs. We want to modify our beliefs. The point is that to modify our beliefs in a simple way, I mean, we want a proper way to modify our belief, and this is given by bias update. So clearly, when I have new information, I should change my belief, but how exactly to do that is not extremely simple, because it has to be done in a proper mathematical sense. So let's deal now with one case. So since we said that two arms are completely independent, now we consider just one arm, and we consider only the case of a Bernoulli distribution. So we know what is the probability of a success given a state, which is called likelihood, and which is the Bernoulli distribution. So again, we know that if we are in a state and we find out that we have a result, this is just this formula here, which I already said many times. Then let's say that I have a belief, so I have a prior, so I already have a distribution of probability over the state. The bias rule gives us a way to modify our belief. So the new belief, so the new distribution of the probability over the state, given that I had a result, it's done by multiplying the likelihood, so the probability of have seen that result given a state, multiplied by the prior, so probability of being in that state. Okay, and then there is a normalizing factor, which we just makes it the probability, so we don't care. So as you can see, the new belief is just the old belief multiplied by the likelihood. Now you can already see where this conjugate distribution enters. So the new belief is the old belief multiplied by something which is of the form to the Q to R, y minus Q, 1 minus minus R. So you can see, or you can imagine that, as pointed out yesterday also, if you have a belief in a form which is not transformed by multiplying by this likelihood, you can remain in the same functional form of belief even with some bias update. In particular case, the general space of belief, it's a mess, because it's all positive function that sum up to 1 in the whole state, or integrate to 1. So in general, it's a complete mess. But for belief that have the special structure of being a beta distribution, then we will see that things are much easier. So what is a beta distribution? Beta distribution is just one possible distribution, which is given by two parameters. So for each one-dimensional degree of freedom, you have two parameters, alpha and beta, and the belief of the state parameterized by alpha and beta is just q to alpha minus 1, minus q beta minus 1, and then again a normalizing factor. You can see that now this beta function is a very similar functional form as on the likelihood. And in particular, what happens, let's say my belief, for some reason, it's as a beta form with alpha and beta, and then I do one observation and I got a success. I could have got a success or I could have got a fail. I got a success. What is my update? My update is that I have Q, this is the first part is the likelihood, so Q 1 minus Q to the 0, and then I have my beta, and then I have normalizing factor. So this just means that my Q, which was to alpha minus 1, now it's alpha plus 1 minus 1, and the beta, and the part with beta stays the same. So you can clearly see that this has first, the prior was a beta alpha beta, sorry for that, and the posterior is a beta prime, so my new belief updated due to the fact that I got a success is just the beta, but in a different point, alpha plus 1 and beta. Okay, so if you start from a beta distribution, so if your belief is a beta distribution, then if you do a bias update, you end up in a beta distribution. We will see in a certain point that if you do not start from a beta distribution, then things get ugly again. Luckily for us, the state of complete ignorance is a beta distribution. So the flat probability, one everywhere, so which says I have absolutely no prior bias of where my state is a beta distribution. It's a beta distribution of alpha equal 1 and beta equal 1. Okay, so whenever from now on we assume, and this is an important fact, okay, we assume that the beginning of so before having any outcome, I could be anywhere in the space of state, and this is mathematically focused in the fact that my zero belief, so the starting probability of being in a state, it's 1 everywhere. It's a flat probability, and it's equal to the product, because they are independent, beta distribution for Q1, which is alpha 1 equal 1, beta 1 equal 1, multiplied by beta Q2, alpha 2 equal 1, beta 2 equal 1. Okay. Okay, so first part of code after half an hour, because this is more like it's not exactly a coding exercise. It's like more a concrete example of something which is a theoretical, more abstract. So what I do now, I just created this very simple thing here, which plots a belief state. Okay, so this is not even coding. It's just that. Fortunately, the beta distribution are useful enough that Python already has them inside. I have a probability density function now. Definitely not now. Okay, so the two beta, I just define the bin, I just define the plot. And okay, so this is just something which allows me to show what is the belief given the two alpha, beta, okay? So let's start with what I said was the total ignorance. So the total ignorance, we said that is when I have alpha 1 equal 1, beta 1 equal 1, alpha 2 equal 1, beta 1 equal 1. And indeed, I have a perfectly flat distribution. Okay, so now we can play around a bit with this. So let's say I pull arm 1, okay, and I get a success. So what is the update? If anyone wants to intervene, now it's a good time. So this is a real question. What is the update? What changes if I pull arm 1 and I get a success?
Alpha 1 become 2.
Alpha 1 equals 2. Perfect. So you can see what happens. My belief has changed. Now you can see that my belief in Q2 is still homogeneous. I have no information on Q2. So every vertical line is perfectly homogeneous. So there is still no information on Q2. But of course, now my belief state says, okay, you know what? I don't think you have a very, very, very low probability in the one arm. Okay, so the belief state has shifted. What is the incredibly helpful thing of having a conjugate description of like this? That here you have to plot a 2D function. Here you have 4 numbers. Okay. So given that we are in the special thing that Bernoulli and beta distribution are conjugate, and our prior was complete flat ignorance, now we have a proper way to translate this belief space, which were a function over 2D, to 4 numbers. Okay, this is what I say much better now. So the belief which contains our current knowledge is what we have to exploit to make the best policy I can. And we have a very simple tool for the belief update. And exactly as before, before I just did 1, now we have just the 4 rules. So if I start from alpha 1, beta 1, alpha 2, beta 2, and I do action 1, then I can only change alpha 1 or beta 1. And of course, I change alpha 1 plus 1 if I have a success, and a beta 1 into +1 if I have a fail. And the same as for the arm 2. If I do action 2, alpha 2 + 1 if I get a success, beta 2 + 1, you know. Okay, this is just a way to move from a belief state to another belief state. Okay, so if I was in a belief state in which my information so far was that I got that number of successes, that number of fails, a single unit of new information would bring me either in one of these 4 directions. Okay. Okay, good. So what was the history, which yesterday you said, what is the history that determines, that shows you what is your current belief, the sufficient statistics of your history, which gives, which are written into your belief, is just the number of wins and number of losses so far. Okay. If you started from total ignorance. So now, a small thing which can backfire is that now we will do, this was in the belief state. So what does it mean from the point of view of having real machines, single points real machine, which can give me one and another? So right now we are dealing with belief. So we always integrate over all possible state inside my belief. Now I want to show you that it's exactly the same thing if you do a proper trajectory with given states. Okay, so then if you have questions, please do. I'm doing the other thing around. So I will do this. I will say, okay, let's take all the history with 6 steps. Okay, then let's take 200,000 randomly chosen states. So for 200 times, I take one particular point in my space state uniformly. So I have a Q1, a Q2, and then I extract for 6 times either a fail or a success. Okay. So instead of dealing with belief, now I'm doing the frequencies part. So for 200 times, I just take one single 2-arm bandit and I say, okay, let's do it 6 times. Then I count how many times it had a success, how many times it had a fail. Okay. So these are all different machines which have different probability of doing that, but all of them together arrived to a single point, which is described by what? It's described by alpha = 5, beta = 3. Okay. Since I started from a completely uniform description of the word, each of them is completely different, but I chose only those which end up in this point alpha = 5, beta = 3. Okay. And then I save only those which arrive there because others have clearly gone elsewhere. And I do, okay, what is my distribution of, if I arrived in that point there, what is my distribution in the Q space? Okay, I just take all the points which arrive there. I write myself what is the Q, and I do, okay, let's do an histogram of this. Do you have any question about that? I assume no. Okay, this is still calculating. Okay. What I'm plotting here. So above, I have an histogram of all the state I chose randomly, and I follow them. Okay, so these are not beliefs. These are a real machine. I chose them randomly, but then I select the probability following exactly what they wanted to do with their very exact probability bernoulli. Okay, and now I chose only a point, which was alpha 5, beta 3, and I saw where did they come from, and this is the description. And then I can do the opposite file. So what is the belief? So the complete abstract belief, which is encoded by alpha 5 and beta 3. starting from ignorance is this one. Okay, so you can see that belief is rather powerful thing. It's an information, it's a complete information of where you could have been, okay, for all the states. Okay, so to summarize, we have this very simple problem here, which we know everything except for the states. We go into the belief, which are distribution over the states. This distribution over the states can be used in a simple way because their updates following bias is simple for two reasons. The first reason is that I put myself in a beta distribution at the beginning. And the second reason is that if you put yourself in a beta distribution at the beginning and you do an update, then you still end up in a beta distribution. For the very simple reason that a beta distribution formally is very close, is structurally the same as the likelihood. Okay, so this here and this here deal well together because multiplied they get again a beta distribution. What we mean, and this allows us to have a transition. So whenever I am in a beta and I know the next outcome, I know where I'm moving to. What this means, and I wanted to show only the same thing. So we said many times now that if you start from a beta function, you end up in a beta function. And this was here. Okay, so I chose Q randomly from 0 to 1. Let's say I don't want to do that. Let's say I want to take them, okay, not randomly. I want to take them in another way. And for example, I just, instead of taking randomly, I just do this, okay? Instead of having from 0 to 1, I'm taking from 0 to a half, okay? So it's the same as before. I'm taking randomly, and I'm collecting only those with an history of 4 success and 2 fails. And my question is, can I describe this with a beta function with alpha equal 5 and beta equal 3? No, okay, because alpha equal 5, beta equal 3 is a good description of my belief for 4 success and 2 losses, only if I starting from beta 1 and alpha 1, which was my total ignorance. Okay, so from now on, you can think of alpha and beta as a description of your history, but you also have to be reminded that this works only if you started from a total ignorance or beta 1 and alpha 1. Okay, so.
Just a small side remark. In fact, in the Bayesian literature, these parameters m and n are called pseudo counts. Okay, in order also to distinguish them from the fact that these are not really sample counts. Okay, they are called pseudo counts because depending on where you start with the prior, they can take different values. Okay. So always keep in mind this distinction between what is Bayesian and what is frequencies. The two things are consistent at the level of beliefs, but you have to be careful, okay?
Yeah, exactly for this. If you want to get a bit confused, and we all want always to get a bit confused, you can say, okay, I don't want to start from total ignorance ever. I want to start from a system which is very skewed in one part. I want to start from a beta which is 6. I want to start from this. Okay, I don't know why. And then I do the same thing. Now, these pseudo counts, M1, N1, will lead. So if you have a beta which is 20, 15, 15, 12, then clearly the number of success and fails need to be related to these numbers. I think this is what Antonio was suggesting. Okay, so good. Now I think we will make a break. If you have questions, please ask. And then we will exploit all these new ways to deal with belief, and actually translate this problem into a MDP, which we know how to solve. If you have questions, otherwise, I think we can make a break.
Yeah, maybe we can reconvene at 10:05. Okay, sounds like it. Sounds like a yes. See you in 15 minutes.
Sorry.
Yeah, Manuele, could you please
yeah, sure.
pause the recording?
Yes. Okay, so good. Let's resume. I resume the recording. Let's share the screen again. Okay. Okay, so we have arrived to a compact description of a belief. So as we saw, belief is a distribution of relative states, but now we have a compact way of writing what is the belief, assuming a prior of total ignorance. So now the space is defined only by these four pseudo countings, n1, m1, m2, m2. Let us imagine that we have such fails and successes, and then my belief can be perfectly described by a beta function using these four parameters. So we can use these four numbers here to rewrite everything as a marked decision process. So from now on, what I will use the term belief or state in a hopefully not so confusing way. I will perhaps say it's state because the ES are the states of a new marked decision process, but I will write B. It means that this new state are actually beliefs. Okay, so we went from a POMDP into an MDP into this new space. Okay, so the new space for this MDP are this belief and can be described by these four numbers here. This means that we've created this mapping from what it was a complex function in a 2D space to a single point in this new four-dimensional spaces of belief. Okay, every single point in this lattice corresponds to a belief. And you can see there is 1, 2, 3, and there is also a fourth axis going in the fourth dimension, as clearly visible by the wriggling of a gray arrow. So if we want to construct an MDP, we need this usual the usual properties on MDP. So we need states, we need the transitions in the state. So a transition now, it's exactly as I was saying, Antonio. So it's let us, as I see a hand.
Sorry, we are looking at a PDF file. Is that what you want?
No, sorry. This because I wanted you to remind that I will put also this lecture was done previously by two colleagues of mine, and I wanted also to point that I will put in the folder also this PDF here, which is essentially the more technical parts of the class. But this is not what I wanted to show you. But this will be, so this you can see now it's the same, but now everything is defined, properly defined from a mathematical point of view. Thanks for reminding me, but now I have to change my sharing. So I apologize. And I will share this screen here. Okay, sorry. Okay, what I was saying, can you see now the usual? Okay.
Yes.
Sorry about that. What I wanted you to show that we went from a function into D, so what we have on the left. Now it's a single point in this lattice of 4 dimension. Now you can see what I was meaning by the 4th dimension axis wriggling in gray into the unknown. Okay, so what was before a distribution function, now it's just a single point. And this also, what was I meaning that now I will use B, but I will call it state, because the beliefs of the old PUMDP now are the state of our new MDP. We need everything to define MDP, so we have defined the states. Now we have to define the transition. So let us imagine that we are in a state of belief given by 4 numbers with pseudo counting N1, M1, N2, M2. Then let us assume we do an action. Okay. If I assume to do the action 1, I can have 2 outcomes. I can have outcome success or outcome fail. Okay. What is the probability of having a success if I have in a belief state N1, M1, N2, M2, and I do action 1? Well, it's actually given by the average probability, which is the essentially it's given by this formula here, which is N1 plus 1, which is the past. It's the past pseudo counting of successes divided by N1 plus M1 plus 2, which is the old pseudo counting in a sense. Okay, so you should and you could do it mathematically. So if you integrate over all the states weighted by the belief in the state, and you ask in each of these states what is the probability of taking action 1 and giving a success, but in the end the result is very simple, and it's just that it's this here. Okay, in a sense, this says that the mathematical result of being in a state of belief of these numbers and doing this action and having a success is given by how many success you already had. Okay, so but this number here is the result of the integrating of all possible state you can visit in that belief with that with probability given by that belief. Okay, but this just means that if I am in a state of belief and I do the action, I can calculate what is the probability of my result. And so I can calculate what is the probability of ending up in a different state. Because since a success from a state of belief, N1, M1, N2, M2, brings me to N1 plus 1, M1, M2, M2, okay, I can calculate that this is the transition probability of being in that belief state and doing that action and getting that result. Okay, so I have only 4 possible outcomes. If I take action 1, I can only change my belief of the probability of arm 1. Okay, so these 2 first lines. If I take action 2, I can only change my belief on Q2, and the change is actually very simple. So with the probability which comes out from my previous belief, which is, so the probability is given by this part on the right, I will end up either in a system which have N2 plus 1 or in a system with M2 plus 1. And one, I will end up with the probability of having a success, and the other one I will end up with the same probability of having a fail. Okay, which means that I'm actually always moving from each point. I can only move in 4 different directions. If I take action, if I consider only the arm 1, I will only move in the plane of in this plane here where only 1, and in the other case, if I take arm 2, I can only move to the 2 different points in belief connected by the 2 different axes. Okay, but this means also, which is something nice, that as you can see, you always move from a state with a certain sum of pseudo counting to a state with a sum of pseudo counting plus 1. Okay. Again, this is nothing but my new transitions in my new MDP, which is my MDP of beliefs. Do you have a question about this? Okay. As I was pointing out, in the PDF, you can have perhaps a more detailed and technical discussion of how this integration works. But I hope that at least the general idea is not too much counterintuitive view. So the new rewards, I have to calculate the function rewards given a belief. And actually, they are the same as the transition. So if I'm in a state of belief described by N1, M1, N2, M2, my probability of having a success is given by this number here. My probability of having a fail is given by this number here. So of course, the reward function is connected by that. So in a sense, this is my function. So it says that the reward if you go from a belief to the next belief, it's 1 only if I'm moving to the belief where I have had a success in N1, in the arm 1, or it's 1 if I have if I'm moving from a belief of N2 to N2 plus 1, which is where which correspond to a success in M2. Okay, so we have defined everything we needed for a new MDP. This new MDP have states which have these 4 integers. These 4 integers correspond to a perfect belief of our correspond perfectly to the belief I have of my states given the pseudo counting. I have the action I can take, which I can take arm1 or arm2. I have transition probabilities. Depending on belief, I have different transition of success of fail. And this lead me, as we've seen, from 4 integers to 4 integers, which only 1 is changed, and it's changed by 1. Okay, so it's like a grid word, but I can only move in a line along the. I can only increase by 1 my total number of integers. Okay. Right now we have defined a problem, and if I gave you this problem here without saying where it comes from, you could have already solved it, because this is just a MDP and we want to solve it. Okay, so what we want to do, we want to optimize the value function of being in a belief, which is none other than taking the value is if we take a policy. So if we assign to each belief an action to take, we start from the bit 0, which is my prior beta of total ignorance, and we go on and on following the policy, and we just accumulate we want to see the expected value of all the possible outcomes discounted by gamma. Okay, which is standard definition of value. The optimal equation now is that the optimal value is the one in which you for each belief you take the best action, which the action which maximize the immediate reward you get plus gamma the value of where you end up. Why is this so similar to the standard MDP? This is a product of the fact that we chose this special Bernoulli problem. So the Bernoulli and beta helped us with reducing the state space, and also that with the whole transition probability of being going from S to S prime was trivial in the sense that you don't move. So essentially, those properties there allowed us to rewrite it in something which is an MDP with no problem at all. Okay, so if I am in a state of belief, I can take action 1 on action 2. This action with some probability will give success or fail, so will give us some rewards. and they will move us accordingly to a belief which has either an n plus 1 if it was a success, or with some probability will move to an m plus 1 if it was a fail. And then I just check, okay, this was I chose the arm1 and I have this expected result. I can choose arm2 and I have this expected reward. Which arm is better? Okay, I will take that. And this is just the way, the usual way it's written, the optimality for this values function. Again, simpler, what is the best policy is just that which maximize this thing. So, okay, you do a value for being in a belief and doing an action, and you take the best one. Okay, so in this way, we are left just to computing this value function. We encounter now a small problem which we have not encountered before. So even if the system is exactly as solvable as before, we have this problem with now the state space is infinite. What does it mean? It means that we saw that the beliefs were composed by 4 integer numbers. Unfortunately, these 4 integer numbers can go to infinity. Okay. So there is no way to make a proper tabular description of the problem, because now I would need infinite for the matrix. Okay, but so this, in a sense, is something which it's this from now on. It's not a problem of the fact that we are in pure MDP. It's a problem which can happen normally solving any MDP, which is the problem. Okay, what happens if I have an infinite set of state? Now enters the good thing, which is we've seen before, which is transitions. As we saw here, you can see transition from a time t to a time plus 1, t plus 1. Always add 1 to some integers. Okay, so we start with a prior which is described by beta 1111. Okay, which is described by n1 equals 0, m1 equals 0, n2 equals 0, m2 equals 0, and then we go away from the origin. Okay, so the total number increases always. If we have a depletion of a discount factor gamma, then if we are interested in what happens at the origin, of course, following rewards are always discounted by this gamma. So and we are always going in the same direction. So we can say, okay, let's create a boundary far enough from the center, and I will be sure that I will have spent so much time around there that the rewards from there on will be so insignificant for my value, which I can discard. Okay. In particular, this is what we do. So we say, okay, let's say, okay, the gamma, the weight of being gamma from a time larger than that boundary time, it's gamma to the t. So because all the time you get gamma value, gamma value, gamma value, gamma value, gamma value. So if you do it t times, this is gamma to the t. I say, okay, I don't care with the tolerance of epsilon. And then you say, okay, if I decide some epsilon, which is my tolerance, which I don't care anything smaller than that, I can choose a boundary length t equal, just you can do it epsilon equal gamma to the t equal log epsilon divided by log gamma, which just tells me, okay, I only need to limit myself to this state, to this group of state, subset of state here, and then I know that discarding the actual result above this t will lead me at most to an error of epsilon. Okay, so we just define the subset of beliefs defined by this integer such that the sum of integers arrive to t. Okay, why is this? Again, because if you remember, at any you can change all four of the integer numbers, but only by one. So every time you spend there is a new extraction, the sum of the integers goes up by one. So in a way, this is similar to what we've done the first time, which we went from the end and we moved back by 1, 1, 1, 1. Okay, so only this. So we had all the collection of the state at each time, in a sense. Okay, if you remember the traveling salesman, you had all the states with 0 cities left, all the states with 1 city left, all the states with 2. Now we have all the state with t extraction of t imaginary extraction, all the state with t minus imaginary extraction. So these are slides of states all condensed together. The only point is that with the traveling salesman, the endpoint was just 1 and was perfectly defined. So we knew the real value from the last city because it was just the city to go back. Now, that point there, we just say, okay, you know what? I don't care. That value there, it would be taken with an approximation, because even if I'm wrong there, that error there will be smaller than epsilon, and I don't care about epsilon. Okay, do you have problems in this? So this is a general way to deal with system in which you can define clearly an arrow of time, and you have an infinite dimension of spaces, but you decide to put a cutoff. Okay. So we use the Bellman equation, as we know. So we just use we take the we just want to do the usual, so the optimal value of the function in a belief, but now we restrict ourselves to our subset we want. You have to do a one of two actions, and this one of two actions, since the number the subset are perfectly stacked one of the other in time. So if I want to calculate the optimal value for a belief which is at time t, so in this subset in which the sum of all integers is t, then I will only need to worry about states which are at t plus 1, because my probability of sorry, this was a b. I apologize. My probability of moving is only and getting a reward is only non-zero if I move from the sum of t equal sum of integers equal t, sum of integers equal t plus 1. Okay, which basically says that to compute the value of state b, one needs to know only the values of state b, t plus 1. Okay, as we said, we took the boundary bt. So the boundary in which the total sum of integer is such a value, capital T, which is what our tolerance is. And then we can just do what we did last time. So we go backwards. So we assign a value to B, to the boundary values, and we go backwards and backwards and backwards and backwards. Okay. As the traveling salesman, going backwards and backwards, looking for the best action between 1 and 2, will give us the best optimal way. In the first update, we have the best optimal option action only for the boundary. Then we have to the state below the boundary, when 2 states below the boundary, 3 states below the boundary, and at the end, we will have the optimal action up to the center. So now, something which we want to point out. This is the optimal policy for each state of belief, as is unique. So we will have for each state of belief a unique action to do, because also it's deterministic. Okay, so we will have, it's not like we will have solved one of the possible, we have solved all possible cases of all possible beliefs cases. Okay, we have solved all the issues which can come up if I assume that I have a complete ignorance of the first in my first belief, and I have some history of pseudo counting. Okay. Okay, how to do it properly? This is now the code. First of all, we decide, as we said, we have infinite states, so we have to limit ourselves with a cutoff. We decide that our tolerance is some value. We know that the discount factors of the rewards in the future are discounted by this factor here every time I move. It's 0.9, which allows us to have a t, which is just this our cutoff boundary. Okay. Okay. So essentially, this gives us 87 steps. Okay. So we will have to compute every step, every state of belief in which the sum of the integers is up to 87, and then we'll say, okay, from now on, we don't care anymore. This is a lot because, of course, we have to create a way to enumerate all the states at a certain time. So again, if you remember, since all the integers can only go up by 1 every time, so we want to enumerate every time, every state possible at a given sum. And this is what it does. So you see, okay, I want to enumerate all the states in which the sum is 5. And essentially, this is what it does. So it says, okay, let's keep track of the states. Let's go from all the states up to the number there, from all the states except what I have, because the sum has to be 5. So this is just a very stupid way to enumerate all the possible combination of integers which sum up to a certain number. Particularly if you do, you can see that you want to do all the states which sum up to 5, and now you have all the states which are sum up to 5. Okay, if you want to be sum up to 10, you have a good number. Okay, so I will not show you 87, but you can imagine that this is quite not cheap in memory. Okay, so what to do with the boundary? So we said that the boundary, we don't care about the boundary, but actually we do something which we have some information on the boundary. So the boundary is the state of belief. Instead of doing, okay, we do the optimal thing, we do the suboptimal point. So in the state of belief of the boundary, which are those in which I have made T pseudo, I have T observations, so T percepts in a sense. I can do, okay, you know what? I will act on the arm, which is my belief it's better. Okay. So since I have a belief on the two arm, I can say, okay, I will exploit this information. It's not now I don't care about what is the variance of the belief. It's just, okay, I have that belief, which is, my belief, current belief is that on average, one arm is better than the other. I will do that. Okay. And this is done here. So if I enumerate all the states at the boundary, so sum over integer is t, and for all the states, I just evaluate what is the probability of success given arm 1, the probability of success given arm 2. And I say, you know what? I define the value, which is wrong, but it's a good approximation. But again, the error will be diluted going back. And the value is just the best of the two actions. Okay, so I will exploit my current belief there, and I don't care what happens afterwards. This is my last state I'm carrying. Okay, and also the next action, of course, is going to be pull that arm there. Okay, and then simply, as in the traveling salesman, you say, okay, I now it's not in the traveling salesman, you really had the optimal value for the boundary. Now it's not an optimal value, but it's an approximate optimal value. But we don't care. So the next step is to iteratively propagate the values from this fake optimal value at the boundary towards all the states with capital T minus 1, and then again. Okay. So if you get a state, you can understand what is the value, because you know now for the two independent arm, you given the belief of the state, you have like probability of win. Given the belief of the state, you have a probability to win with the other arm, and then again it's the probability to win. Then I have the reward of winning plus gamma multiplied by the value. Since I was arm 1 and I won, now what is the state new state of belief I'm going to? It's state 0, so it's n1 plus 1 and 2 m1 and 2 plus this. What is this way is probability of failing. I don't have 1 because I failed, so I do not have a direct reward, and I have gamma multiplied by the state, the value of the state of belief, which is the same as before, so n1 and n1 n1 and 2 and 2, but now my pseudo counting of failing is plus 1. Okay, so if I imagine to be in a state of belief n1 n2 m1 m2, the probability to win is this. Okay, and where I end up in a belief, if I imagine to be in this belief and I win, is this. Okay. So this is none other, these two lines for arm 1 are not none other that if I took action 1 and I do sum over the new state, this here. Okay. So I'm literally applying the Bellman optimal equation, because I am assuming, and this time is only approximating, it's not 100% accurate, that these values are already optimal, because they lie at a higher level. They all lie closer to the boundary. I'm starting to the boundary, and I pretended those were optimal, and I go back and I pretend those upwards in the flow are optimal. Okay, so I have the quality, which means what is what is the cumulative discounted value of doing arm 1, cumulative discounted of doing arm 2. And then of course I have 2, I can compare, and I will have its information, so I can do okay, what is the best one between 1 and 2, and what is the arm I should pull. So it just returns what is the best value in that state, in that belief state, and what is the best action to do in that belief that deals with the state. Okay, so this does only for one belief state, but now I have to do it all the belief states starting from the boundary downwards, and this is what I do here. Okay, I start in range T, so I'm excluding T, I'm going up to the boundary, and I'm going backwards. This is Python way to say I'm going backwards. So I get all the states at that point there, and for all the state in this, and for all the state in this subset with the sum of integer arrive to T, I just say, okay, what is the best value? What is the optimal value? What is the best action? And I store it. Okay, and I've done everything, and this is essentially solving my issue. I had to do this before. I should always. Yes. Sorry, I forgot that I had to restart everything. So, okay. Good. Okay. So once I did that, I have the perfect solution, and at least in the limit that I have fixed the cutoff. Okay. Do you have a question about this? Okay. I assume everybody is more or less desperate. Okay, so we can now check the numbers of this. So good. Let's, for example, let's plot a solution. So okay, this is just what happens. Okay, so I took this T, capital T, as before. This was already computing all the values and best action. Okay, this is just a script to properly plotting it. And now what I have actually the solution for n2 equal 5, n2 equal 5. Okay, so since the hyperspace of belief is 4 numbers, it's very hard to make any reasonable plot in this space. So instead we say, okay, we fix n2 equal 5, n2 equal 5, which means that my current belief for Q2 is a belief which is more centered to fairness, because this is equivalent to a history of 4 success and so it's a belief which is it's more or less centered in the center. So I have not a strong belief, but I have a belief of a fair coin. And now I'm looking at all the possible other state of belief for the other arm. Okay, you see what I'm doing. So the value is what I expect my value to be in the future if I start in a belief which is characterized now by N1 and M1. Okay. Now, and this is the best action to take. So let's look a bit about of these plots. And if you have specific question about these plots, please ask. Okay, so this is just, I've solved the system with a cutoff rather far away. I've put myself in a situation in which I fixed my belief of the arm 2, which is a not strong belief of fairness of arm 2, and I'm checking in the space of beliefs for the arm 1, and I'm checking what is the value and what is my best action to do. So the value, it already gives us some nice information. You see my pointer, right? Please, somebody do. Okay, good. So look here. So the value, so since gamma equal to 0.1, okay, 0.1, I expect, I have a discounted value which is probably 9, 10. Okay, so that range there. So here, where I have that N1 were extremely superior to M1, I have a very strong value, which means that I am very confident that this is a very biased arm towards the 1. I will choose arm 1 because I see that it's much better, and the value which accumulate is very high. Okay. Then clearly, if you go towards the middle point, so this red region here, it's clear it's a best action to take arm 1, and I take it. And indeed, the value decreases going away from this axis. This axis here is the axis in which I had. It's almost clear to me that I had a super unfair arm 1, which always gives me a success, because I essentially, it's the belief of having seen a lot of successes and very few, it's equivalent to the belief of having seen a lot of success and very few losses. And then when I arrive here, everything is flat for a very simple reason, because I do not expect to do I do not expect to take ARM1, but I expect to take ARM2. And ARM2, I do not have that information, but I know that it should be fair. So now here where is orange, I expect to do ARM2, and I expect that since it's fair, I will have less, I have half of the value of the maximum value. Okay, but this is less important information. But what I wanted you to focus on is this figure here, which I find very interesting. So this is the best action to take. I plotted the green, the yellow line, which is the diagonal line. So every belief above the diagonal line says that my current belief is that ARM1 is better than ARM2, because my belief of ARM2 is that the probability, the maximum probability in the belief of ARM2 is 0.5. Since I have equal number N2 and M2, my maximum probability in the space of Q2 is at 0.5. And that probability there corresponds to the yellow line. So if I am above it, my current maximum probability in the belief of ARM1 is actually better than the maximum probability of belief in ARM2. But you see that there are a non-vanishing small of region where actually the best action is ARM2. Can you guess why? I do not hear anybody. No, I don't know if... Okay, so this goes back to what we discussed at the beginning. So why is this not a trivial? Why reinforcement learning is never trivial? Because we have to carefully balance two drives. One drive is exploitation, which means my current belief is that this is better. I should do that. I should only do that. Never think about anything else in my life. And exploration. So my current belief is that this is better, but my current belief could be garbage. So I should go around. And you can see now, you can see now that here, close to the yellow line, my current belief in the ARM2 is 0.5. My current belief in ARM1 is slightly above 0.5, okay? But as you can see, my belief in ARM1 actually comes from hyperparameters. For example, where I am at, it's like 40-40, okay? Maybe it's 35-30, okay? Which gives me a very strong belief that my arm has a probability centered towards a value which is 0.5, but it's also very narrowly centered. But now I have a belief in ARM2, which is actually centered in 0.5, but it's actually quite weak. We can plot it now. So we take 35, 35, 5. Let's do it. Okay, so this is our current belief. This is exactly the belief we are here somewhere. I mean, somewhere, okay, close to that. And you can see that the best here, it says, oh, clearly the maximum of its probability is above 0.5. The other one is in 0.5, so exploitation is better. But you can see that actually there is a very considerable amount of probability of being in a system in which Q2 is actually above the diagonal, okay? It means that for this specific region here, the best possible action is actually to explore Q2, because there is a very reasonable probability that it ends up in a state in which Q2 is actually much better, okay? This form here exploitation and exploration. So this small tongue of blue curve there is why we need reinforcement learning. If you did not have that, your value would be smaller. Okay, and this is essentially the point of reinforcement learning. You find a compromise between exploration and exploitation, which is not at all easy to find in other ways. Okay. Now I wanted to if I have a few minutes left, I want to show this. So far we worked with beliefs. So we have a proper system. We have solved the problem with total ignorance as a prior. So we start with a completely indiscriminate. We could have any state, and we solved in a Bayesian way. So at any point, it's like, what is my current belief? I imagine that I extract things following my belief. I imagine that everything follows my belief, and this is what happens next. And we have a solution for this kind of thing. So this is the optimal solution if my world is completely Bayesian. So if I assume that at each time I will have a randomly distributed following the belief. Okay. But then we started from a very different point. We started from, this was a frequentistic problem. We have one, I've been given 2 coins, so they are there, and somebody wanted to know what is the best thing to do. In this particular case, the solution for Bayesian can be applied. So we have a perfect optimized set of actions for each set of beliefs, and actually applies even if I do what is generally not the same thing. So I take one single case and I truly flip the coins, and depending on the flipping of the coins, I decide what to do next, which are not the same thing. The Bayesian part is I take beliefs, I take all possible states which are compatible with that belief, and I follow all of them. Okay, it's a much larger one. But in this particular case, I can say, okay, but does it work if I also have a simple question, which I have 2 coins and I have no idea what to do? So this is what I want to do now. So I start with a total ignorance belief, but I actually start with a very specific real state. So I start with a state of Q1 equals 0.45 and Q2 equals 0.555. And what I do is actually I take these 2 arms, and the result is fail and win. And I'm doing up to 87 steps. And what I do is I check, I record what is my history of this particular specific thing. So this is not a belief anymore. This is just one history of one instance. And I take the best action to do, the best action that I want to do following the solution in a Bayesian sense. And I just take the result of a random polynomial with the Q1 I know that is there, and I either take arm 1 or 2, I collect the history, and I'm in a new belief system, new belief world, and I use that belief for the optimal solution for that belief, and I apply it to my concrete example here, and I see where it goes. And where I go is, okay, I begin, I was in ignorance, I pull the first arm, and the result was fail, so I got shifted there. Then I pull the second arm, and the result was a win, so I got shifted in that corner there. But I pulled again, the result was a fail, so I got shifted there. Then it was a win, then it was a win, and then I go, And at the end, ends up, is this the proper? Okay. It ends up doing the optimal thing, which is the second arm. And you can see now it has also, it's rather strange, but it's true. They're also not explored much, but it is sufficient for him to be here. Okay. Have I, perhaps I should have taken, wait. While I do this, do you have questions?
Sorry,
Yes.
is there a way to make the model more explorative or more exploitative?
Well, for example, Antonio was proposing two models which are extremely explorative or extremely exploitative. So a perfectly exploitative model would be to choose the arm which has the maximum probability of success.
Sorry, Morale. Let's call them strategies.
Strategy. Sorry. Strategy. And the other strategy which is properly explorative is, for example, choose the arm which has the largest for example, the least number of trials. Okay, you all times choose the arm in which you have the least number of trials, because that means that your information is lower, or you can do other information things. But this is strategy, but those are worse strategy than this. This is by definition the optimal strategy, combining exploitative and explorative strategy. Was this the question? Because I'm talking about strategy, you were talking about models. Is this the question? Was this the question?
I was thinking if there was the possibility to set a certain kind of threshold that for choosing the strategies.
Well,
I'm not sure I understand the question, but maybe I can try and clarify some points. So you can construct very different kinds of heuristic strategies, like the ones I said before, which are definitely suboptimal, so too exploitative or too explorative. There are other strategies. One of them very famous is called Thompson sampling. Thompson sampling, what it does is just looks at the belief, the current belief, and then extracts one state at random according to the belief, and picks the optimal action for that state. Okay, this is a heuristic strategy, and it's a good heuristic strategy, but still it's suboptimal in the Bayesian sense. That means if my states are picked according to my prior, then the strategy that you find here by solving the Bellman's equation is probably the best one. What is not obvious in general is that if you use a Bayesian strategy with a certain prior, uniform for instance, but your world is giving you coins according to another distribution, then these two things need not necessarily have the same performance. Okay, so it's important to first clarify the distinction between heuristic and optimal strategies. Okay, heuristic strategies you can construct, but they are lower in performance in the Bayesian sense. There is given that prior, they have a worse performance than the optimal Bellman. First thing. Second thing is that any strategy you come up with, the Bellman or the heuristic, okay, are more or less well suited to that prior. And if you compare them with other priors, with data coming from different initial distributions, they might have different performances. I hope this clarifies some of the things. Otherwise, you can try and reformulate the question.
So in the end, we choose the best. We choose the best policies that that combine the best exploitation and the best exploration. So we can't choose in any way how to force the policy to follow a much more exploitative model.
Exactly. For that given prior and for that given model, that's the best thing to do.
Okay, and we can't force to move our policy toward our.
If we do that, we lose in performance. If we force it to be more exploitative or more explorative, we will have a lesser expected gain. Where expectation, remember, is always done over beliefs.
Okay, thanks.
Sure. I think we can wrap up because we're running too late unless there are burning questions. So I think, as usual, you will find the notebook on the Slack channel as soon as Emanuele has some time to upload it. And otherwise, we'll meet again on next Wednesday for the theory lesson. Okay. You're muted.
Still muted.
I think you can quit the recording anyway.
Sure.